Hey guys, this video reviews what I like to call the middle school method of covalent bonding. It's the simplest form of using Lewis dot structures, and it's probably something you've learned in middle school. When your teacher showed you how to make covalent bonds, he or she, I'm sure, did something like this. Well, let's take two atoms. Let's say sulfur and chlorine were reacting with each other, forming a covalent compound, right? We know they're covalent because they're both nonmetals. And they're both going to have, more than 4 valence electrons here. Sulfur is in group 16, and sulfur, being in group 16, has how many? Yep, 6 valence electrons. So we draw the valence electrons around sulfur first by going to the 4 corners. And after we get to the 4 corners, if there's more than 4, we keep going. Sulfur, with 6 valence electrons, has 6 dots shown. Notice that 2 of them are called paired up electrons, and then 2 are sort of lone electrons. Chlorine, when we look at its position on the periodic table, has 7 valence electrons. It's in group 17. So let's draw the number of valence electrons in chlorine. This time, we only have 1 unpaired electron with a total of 7. I drew them in a different color for clarity. Now, what I'm sure your middle school teacher showed you was how, well, look, chlorine has a vacancy here of 1 electron, and sulfur, by sharing its electron here, could fill that vacancy. At the same time, sulfur gets closer to having its 8 electrons, because its vacancy is filled by chlorine. Chlorine gets to 8 by using this shared electron pair, but sulfur still needs 1 more. And when you're reacting elements or atoms together, you're never really dealing with just 2 atoms. You have, many, many, many atoms of each of them. So it's absolutely legit to do the following. To say, well, if sulfur and chlorine are reacting, you have as many chlorines and as many sulfurs as you can imagine to make the appropriate molecule. With chlorine having 7 valence electrons, it can share 1 with sulfur here. This would form sulfur dichloride. There's 2 chlorines. We don't leave this chemical structure normally with dots. If they are bonded electrons, we show those dots as lines. I leave the non-bonded electrons in because, as we learn later, these do affect what's called the three-dimensional geometry, or the shape of the molecule. But this is what's called the Lewis dot structure of sulfur dichloride. It's a valid structure because everyone gets to 8 electrons. Let's review what this looks like up above. When we count each electron in the bond twice, we get to 8. 1, 2, 3, 4, 5, 6 for chlorine, 7, and then 8 with sulfur. 1, 2, 3, 4, 5, 6. Now we count this again because it's being shared. 7, 8. We count this again too. Chlorine, 1, 2, 3, 4, 5, 6. And we count each of these again. 7, 8. So that everyone gets to 8. The only element that, of course, doesn't need to get to 8 would be hydrogen. Let's try another one which might form what are called double bonds. We can start again with sulfur, but this time let's react it with oxygen. Sulfur in group 16 has 6 valence electrons. We go to the 4 corners before we start pairing up. Oxygen also is in group 16, so it also has 6 valence electrons. Immediately you probably see the solution to this problem. Well, if this pair shares and this pair shares, you could form what's called a double bond, and everyone would get to 8. Perhaps a different way to represent it might be with the sulfur and the oxygen here. If they each have their own non-bonding electrons, like this, if we push sulfurs a little bit toward the middle more, you might be able to visualize it better. And if we have oxygens, 6 non-bonding electrons like this, 6 electrons like this, and we push its toward the middle, we can see that you could form a double bond. Each pair shared forms a bond. This molecule is more commonly represented like this, with the double bond in between the sulfur and the oxygen. As I said before, this type of dot overlapping process is the middle school method, as I like to call it, because it works for a lot of simple molecules, but it doesn't work for every molecule. What we're going to talk about later in a subsequent video is a better approach, which will allow you to solve the three-dimensional structure of any type of covalent molecule. Let's just do one more practice. When you think about nitrogen in the atmosphere is in the form of N2. It's nitrogen bonded to itself. And it's a very, very strong and stable bond that exists between them. Nitrogen is in group 15, so it forms, has atoms with 5 valence electrons. Let's take another nitrogen. 1, 2, 3, 4. This time I'm going to show this doubled up pair. Because what if we share these two, and these two? Does everyone get to 8? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. Yep, the hydrogen on the left gets to 8. Let's try the hydrogen on the right. 1, 2, 3, 4, 5, 6, 7, and 8. We count the shared electrons twice. So by forming a triple bond, nitrogen completes its valence and gets to 8. Every bond here represents the sharing of 2 electrons. So this is an example of the simplest way of overlapping electrons to form Lewis dot structures, or just Lewis structures. Again, like I said before, it doesn't work for everything, so we're going to learn a better, little more complex method, but I wanted to review this just so that it reminded you of what you did in the past, and you can still use this for some very simple molecules, but we're now ready to take it to the next level. That's it for this video.